All right, so I took all the pictures you sent me and put them into a PowerPoint so I can annotate over them. Um, so I don't know if they're in the exact same order that you sent me, but hopefully they're in some kind of order that's recognizable to you. So the first one here, how many grams of mercury 2 oxide are needed to form 22.4 grams of oxygen gas? So we're starting with 22.4 grams of oxygen gas. All right, so we're starting here. We want to get to grams of something on the other side of the equation. And so we're going to employ stoichiometry, in which I'll use to get from grams of O2, I need to then go to moles of O2. I'll do that using the molar mass. I'll use the mole to mole ratio or the coefficients to get from moles of O2 to moles of mercury oxide, HGO, and I'm running out of room here. Then I'll use the molar mass of this guy to get to grams of HgO2. So we're going to need to know the molar mass of O2 and HgO. So O2 is 32 grams per mole. Let me real quick look up what HgO is. It is 216.59 grams per mole. All right. So like I said, first, we want to go from grams of O2 to moles of O2 using the molar mass of O2. So I'm going to put my grams of O2 on the bottom because I want them to cancel. I'm going to put moles of O2 on top because that's the unit we're going to. I'm going to use this number here where there's 32 grams per 1 mole. All right, so now I'm in moles of O2. So now I'm here and I'm going to go to moles of Hg using the mole to mole ratio. So I'm going to put moles of O2 on bottom and moles of HgO on top. So my moles of O2 would cancel. For every 1 mole of O2, there's 2 moles of HgO. So I'm getting that from the coefficients. There's an implied 1 in front of the O2. So I'm almost there. Next, I need to go from moles of mercury oxide to grams of mercury oxide. And I'm going to do that using the molar mass here. So I'm going to put moles on bottom because I want them to cancel out. I'll put grams of mercury oxide on top. And for every 1 mole, there is 216.59 grams. All right. So I'll leave that for you to solve, but you'll multiply across the top. You'll hit enter and then divide by 32 into your calculator. All right, so moving on to the next problem here. So, okay, I'm a little unclear why you screenshotted this one because it does give you the setup, but if you want me to explain it, I'll go ahead and explain it. So the problem starts with 29 or 28.9 grams of carbon. So we're starting here. And then they want to know how many moles of carbon dioxide there are. So they want to get here. So we're starting with grams of carbon. We want to end in moles of CO2. We can get we can't directly get from grams to moles of CO2, but we can get from grams of C to moles of C using the molar mass of carbon, and then we can get from moles of carbon to moles of CO2 using the the coefficients from the equation. So they started with their given quantity. All right, so they started with the 28.9 grams. They got out of grams and into moles using the molar mass of carbon. And then they got out of moles of carbon and into moles of CO2 using the coefficients from the equation, which are all implied as 1. Okay. So this problem asks us to solve for how many moles of carbon dioxide will be formed when we start with 0.7 moles of C. All right. So we can go from moles to moles. So moles to moles of one substance, or sorry, moles of one substance to moles of another substance, just using the coefficients from the balanced equation. So I'll start with my given quantity, moles of C. I want to get out of moles of C, so I'm going to put him on bottom. I'll put what I'm trying to get into on top, which is moles of CO2. So this is equation has all implied coefficients of 1. So this problem happens, I don't need a calculator to do this one, but this problem happens to be that 0.7 moles of C equates to 0.7 moles of CO2. Okay. All right. So this one is similar to the last problem we just did. So here it gives us a balanced equation. It tells us if 3 moles of tetraphosphorus decaoxide, which is this substance here, were to react, how many moles would we get of the rest? So basically, right now, the coefficients are 12, 1, 4, and 6, but they're saying what would happen if this coefficient, which was once 1, is now 3. So basically, we're multiplying everything by a factor of 3. So if I multiply this first guy by a factor of 3, I get 36. If I multiply the 4 by a factor of 3, I get 12. If I multiply the 6 by a factor of 3, I get 18. So this reaction would consume 36 moles of the HClO4, 3 moles of the tetraphosphorus decaoxide, but that's what we were starting with, 12 moles of the phosphoric acid, and 18 moles of the dichlorine heptaoxide. Okay. So in the very first problem I did in this video, I Googled the molar masses, but there's a way to solve them. So if you go to the periodic table, right, and this is the PT table, there's values listed under, so like hydrogen, it says the symbol, it says the name, and then there's values listed here, right? These values are the values we use for solving for molar mass or formula weight, molecular weight, molar, there's all kinds of names, but formula weight, molecular weight, molar mass, atomic weight, all the same things, right? So you'll need to so it's asking us to solve for the formula weight or the molar mass of CO2O3. So you would need to, I'm finding these numbers from the periodic table, but the molar mass of O or O2 minus is 16 AMUs. AMU is also equivalent to grams per mole. All right. Cobalt or CO has a molar mass of 28.01. All right. So now we need to take into account how many molecules of cobalt and ion are in this entire formula. And so we'll get that from the subscripts here in this equation. So there's 2 moles or number of ions, I'm sorry, yes, two cobalts in the cobalt 3 oxide, and there's 3 oxygens. So I'm just getting that from their subscripts. So now you would need to multiply across and fill in this guy. All right, so you'll multiply there. You'll multiply across 16 times 3 and fill in this guy. And then you'll add these together to find the entire formula weight in which you'll input there. Okay. All right. Here we are balancing. So the first thing I like to do when I balance an equation is list the elements I have on each side, and I like to list them in the same order. And then I like to get an initial count of what we have. So right now, with implied subscript or coefficients of 1, I have 1 sodium on the left, 2 hydrogens on the left, and 1 oxygen on the left. And on the right, I have 1 sodium, 3 hydrogens, and 1 oxygen. So I need to make these the same by manipulating the coefficients to get these total numbers here to equal. So I've had a lot of practice at this, but on the left side here, I'm seeing H2 always as a pair. I could put a coefficient of 1 here, it's going to be 2. I could put hydrogens. If I put a coefficient of 2 here, it's going to be 4, and so on and so forth. So that makes me think that I need to start by getting this odd number of hydrogens on the right to an even number. So I'm going to start by doubling this NaOH, okay? So that will increase all of my elements that I'm working with, but I think that this is a good place to start. So now I'll have 2 NAs, an additional an additional H for a total of 4 now on this side, and an additional oxygen for a total of 2 now on this side. So now it looks like this side is basically doubles of this side, meaning I could go in here and put coefficients of 2 in front of each of these, and I should now be balanced. So now on the left, I have 2 sodiums, 4 hydrogens, and 1 oxygen. So it is now the same on each side. So they are now balanced. If you write this on a piece of paper, you might leave off the implied coefficient of 1 here, but I'll want you to type that implied coefficient of 1. Okay. Okay, so this is the hardest problem for sure in this first set of vowels, first and second probably. So I should have deleted this problem, but I didn't, because when I first glanced at it, I thought it was one of your learning objectives, but it's really a lot more complicated. So just bear with me. So for A here, we're going to start with our given quantity, which is 2.09 moles of N2O. It's asking us to get to grams of just nitrogen. So first, I need to get from moles of my entire substance to moles of just nitrogen before I can go to grams. So for every 1 mole of the entire substance, there is 2 moles of N, and I'm getting that from this subscript here. So now that I'm out of moles of my entire compound and into moles of just nitrogen, I can go from moles to grams, and I can do that pulling the weight off of the periodic table of nitrogen. So I'm going to put moles of N on bottom because I want them to cancel. I'll put grams of N on top because that's the unit I'm trying to get into. For every 1 mole, there is, and I got to look this up real quick. There is 1401 grams of N, grams of nitrogen. So now it's a matter of just multiplying it by across and dividing by 1 to get your answer there for A. I would round to 3 digits. 3 digits. Sorry. Okay, so for B here, you're doing the opposite, sort of. B is where it starts to go awry a little. So now we're starting with grams, and we're starting with 1.14 grams of our entire compound, N2O, and we want to get to moles of just oxygen. So we're going to go from grams of the entire compound to moles using the molar mass of the entire compound. That's where it differs from the last step in A. So I'm going to Google this real quick. So the molar mass of N2O is 44.01. So I'm out of grams of my entire compound and I'm into moles of my compound. Now I can go from moles of my entire compound to moles of just oxygen. I'm going to put moles of my entire compound on bottom because I want him to cancel. And I'm going to put mole of just oxygen on top. For every 1 mole of the entire compound, there's 1 mole of oxygen. And I'm getting that from the implied subscript of 1 here on this oxygen. So then it's a matter of just plugging it into your calculator, and with all the ones, it looks like you're just plugging in 1.14 divided by 4401. And I will let you actually plug that into your calculator and solve. Okay. So this problem is similar, but a different compound. All right. So looking at A here, we're starting with moles of a certain compound, and we're asked, oh, wait, no, this one is different. Sorry. I looked at it real quick. This is a fun one. This is one where we'll need Avogadro's number. Okay. So we're asked how many moles of the entire compound there is if we're starting with 2.4 moles of just bromine. I don't think we'll need Avogadro. You know what? I should just work it through and then I'll figure it out. All right, so we can get from moles of just bromine into moles of the entire compound by using the subscripts from the compound. So it's always 1 mole with the entire compound. And then it's going to be 4 moles of Br because there's a subscript of 4 with the Br. I put moles of Br on the bottom because I wanted them to cancel and I wanted to get into moles of CBr4 on top. So like I said, I will let you solve, but that's just a one-stepper. All right, so this one, now we're given moles of the entire compound. So we're given 2.09 moles of CBr4, and we're asked to go to moles of bromine. So similar to the one above, I'm going to put moles. I'm going to put CBr4 on bottom because I want them to cancel, and moles of just bromine on top because that's what we're trying to get into. For every 1 mole of the entire compound, there's 4 moles of Br. So again, I will let you plug that into your calculator. All right, this one looks like an Avogadro's number 1. Okay, so the question is asking us how many molecules of dinitrogen monoxide, N2O, are present in 2.09 moles of this compound. So we're starting with 2.09 moles of this compound, and we're asked to go to molecules. So Avogadro's number is 1 mole equals 6.02 times 10 to the 23rd. And I like to say stuff because we can insert here anything that basically the problem asks us. So we could insert molecules, we could insert atoms, we could insert, I think formula units is another one they use, right? So here it applies to molecules, so we can insert molecules. So I want 1 mole on bottom because I want my moles to cancel out, and Avogadro's number 1 is associated with the mole. And then I'll put 6.02 times 10 to the 23rd molecules on top. And then now we're in molecules, which is what it's asking us. So it's just a matter of plugging that into your calculator. B, I see you have an answer typed in. So maybe you've already begun to answer this one. So this time we're just going backwards. This time we're given the molecules and we're asked how many moles is that? So again, we can use the Avogadro's number conversion factor here, where 1 mole equals 6.02 times 10 to the 23rd molecules. So I put molecules on bottom because I wanted them to cancel. I put 1 with mole because that's how the conversion factor works. And I put 6.02 times 10 to the 23rd with molecules. So when you plug this one into your calculator, make sure if you're using like a scientific note calculator or even your phone calculator, that you say open parentheses 6.94 times 10. You might have to use a caret key to the 21, close parentheses, divided by open parentheses 6.02 times 10 to the 23rd. Oops, you'll have to use a caret key, close parentheses. You want to make sure you tell your calculator that, hey, these numbers stick together and these numbers stick together, or else it's just going to employ PEMDAS and give you an incorrect answer. Okay. Oh, and that was the last one. All right. Let me know if you have any more questions after watching this.